Hey AP kids, welcome back to your videos. I know you've missed them. In this video we're going to talk about differential rate laws. This is kind of to me like Hess's Law. Remember how I promised you Hess's Law problems would be sort of fun in a weird kind of twisted way? I think differential rate laws are also kind of fun in a twisted way. So as we're learning these, keep in mind that we're going to be learning the law of mass action. The law of mass action is simpler than it really sounds. Basically what it says is that the rate of a reaction is proportional to the concentration, and molarity of course, of the reactant. Well, we already known that. We've learned that at the very beginning of this unit. We talked about the factors that affect the rate of reaction. So this is well-known stuff. And really what kinetics is concerned with is how do we find out what the proportionality is. Is it linear? Is it independent? In other words, is it zero order? Is it quadratic, second order? So on and so forth, okay? It could be inverse even. So we need to find out what N is. In essence, what we're trying to find is called a rate law. Rate, where rate equals, and we have a constant there to represent our slope. And it's the same stuff we've always been trying to do here. Is if we're looking at concentration and rate, X and Y variables, and we're trying to find that slope. Almost everything we do is linear. It just so happens that in kinetics here, we can get some more complicated type relationships. Zero order, first order, second order, and theoretically even higher. So that's the law of mass action. And there's a couple of ways, a couple of methods that we have to come up with this order. One is called differential rate law. Obviously the title of this video is differential rate law. And when we use differential rate law, it's really a little bit more accurately called the method of initial rates. I'll explain that in just a second here as we continue. The other way we can come up with these orders is to use what's called the integrated rate laws. And we will not be doing those at all in these videos. There will be another video following this about integrated rate law. But back to differential rate law and the method of initial rates. Here's the guiding principle here. We know that if we have rate over time, or graph versus time here, we've seen that the rate of a reaction drops off as time progresses. As the concentration of the reactants decrease, the rate of the reaction decreases. So in this method, we're trying to get the measurement of the concentration right at the beginning and measure the rate right there at the beginning before the concentration starts dropping off. And to get if we do it at that point, then that's like the maximum possible rate at that concentration. And it allows us to use that value as an assumption that it's continuous. Or that doesn't make a lot of sense the way I just worded it. But what we're trying to do is to get that initial concentration right at time zero or very close to time zero and use that calculated rate to find our orders. All right, let's do some practice here using the law of mass action and look at some of these proportionalities. So in number one here, the initial rate of a reaction is 16 times greater as the concentration of one of the reactants is quadrupled. So what is the order of this reaction? We've seen these type of questions before, like when we were dealing with the gas laws. If we double the pressure of a gas, what happens to the volume and stuff? So same action here. Let's look at the math a little bit more closely here. It says the rate is 16 times greater, so that becomes 16 times the rate. We could really kind of ignore K here, but we are going to quadruple the concentration of the reactant. So that becomes 4x And so what happens? What does the order have to be if I quadruple the concentration and get 16 times out? Now, I'm about to do something that's going to make the math wrong here, but I'm just trying to illustrate here more than anything. That means whatever this quantity is here is going to be squared. So I quadruple it, and if it's a quadratic function, quadrupling a quadratic, that gives me 4 squared when it goes to 16 times greater. So that is the answer here. This would be a second order rate law. So rate would be K and then the concentration squared. All right, so number 2, if a reactant has a -1 order, what happens to the initial rate when the concentration of the reactant increases by a factor of 2? Well, using algebra, what exactly does it mean if your order is -1? Yeah, that's the inverse function that we learned with Boyle's law, for example. So that means inverse. Y is inversely proportional to X. In our terms here, rate is inversely proportional to concentration. And so if I double, let me read it again. What happens to the initial rate when the concentration? So if I double the concentration, the rate is going to decrease by half. So divide by 2. Number 3, a reaction A plus 2B goes to C has a rate law given. All right, so cool. You can see the rate law right here. If the concentration of A is tripled and the concentration of B is doubled, by what factor is the rate increase? Okay, so these effects are going to be independent of each other because we assume that whatever A is doing there and whatever B is doing have no relation to each other. We'll learn more about the collision theory and how that works later in this unit. But let's treat each of them individually. A is first order. So A is going to be Y is proportional to X, first order. And B is going to be Y is proportional to X squared. It's quadratic. So let's do A first. If I triple A, 3X is going to give me 3Y. That is what it means to be first order, linear. And then for B, if I double B, again, I know my algebra here is not really kosher, but if I double that quadratic function, I'm going to get 4 times out. Okay, so now we have to combine those. So if one triples and the other one doubles, a triple double, so to speak, is 6 times. So 6 times greater. It appears I do bad math. Thinking about that, that's terrible. I promise I can do math. So let's say that again. One triples, we triple X, that causes the rate to triple. I double for B, that causes it to quadruple. So a triple quadruple, that's what I was trying to say. Triple quadruple, that is 12 times. So a little math error there as I was getting confused. Reading along here, but that is 12 times. All right, then number 4. The reaction methane plus oxygen goes to CO2 plus water has a rate law given. You can see that there is KO2. Interesting. If the concentration of methane is changed from 0.2 to 0.4, in other words, it's doubled, and oxygen is changed from 0.3 to 0.9, in other words, it's tripled, by what factor does the rate change? Well, that's interesting because it asked us about methane, and it's not even in the rate law. So what do we do with it? Well, if it's not in the rate law, that means it is 0 order. In other words, it's independent. The rate is independent of the concentration of methane. So this 0.2 to 0.4 for methane has no effect. zero effect on the rate. It's all got to do with the oxygen. So if I triple oxygen, that's 3 squared. That means my rate is going to increase 9 times. Okay, we're going to pause there and we'll break this video up, and we'll do in the next video some examples using the method of initial rates. So let me know if you have any questions about the law of mass action here.